we have the first fundamental theorem of calculus. It says that if a function f is continuous on the closed interval from a to b, and this big F is the antiderivative of the little f on that interval from a to b, then the integral from a to b is equal to the antiderivative of b minus the antiderivative of a. So let me show you how we put this into use. This first fundamental theorem of calculus is used to determine the area under the curve that we've been doing geometrically and with our properties. But we can actually find our antiderivative and then calculate the area under the curve with our a and our b. So first step is to actually take the antiderivative of our function. So remember, to take an antiderivative, we add 1 to the power, so we would be at 3, and then we divide by that. So that would really look like 1/3 x to the power of 3. Or you could do x to the power of 3 divided by 3. So that's the antiderivative. Normally we would put a plus c here, but this is a definite integral. The plus c is for an indefinite. We have the values that we want to know from here to here. So it's the area under the curve from 1 to 3. So what we're going to do with that is we're going to take 3, that's our b value, that's our upper limit, and we're going to substitute it in. So this equals 1/3 times 3 to the power of 3 minus f of a. That's our lower limit. So 1/3 times 1 to the third. Now I'm going to simplify that. And this is 1/3 times 27 minus 1/3 times 1, which I don't really need to write. 1/3 times 27 is really 9, so 9 minus 1/3. And then you could make common denominators, and this ends up being 26/3. So the definite integral from 1 to 3, the area under that curve, can be calculated with that f of b minus f of a, the fundamental theorem of calculus that we just did. So the area under the curve from 1 to 3 is 26/3. So I'm going to let you go ahead and pause and find the antiderivative of this just as practice. Okay, hopefully this is what you got. Now I have from 0 to 4 that I want to find the area under the curve for. So from 0 to 4 are my upper and lower bounds. So we take the upper bound and do f of b, so 2/3, 4 to the power of 3/2, plus 2 times 4, so substitute 4 into all of this. And then we're going to subtract, and be careful because you need to have all of this in parentheses over here, this with 0 substituted in. Well, hopefully you recognize that we don't really need to substitute 0 in, because anything times 0 is really just 0, but I'll write it just for showing our work. But this is really just a value of 0, and minus 0 is not going to change anything. So really we're just dealing with this front part. So 4 to the power of 3/2, that gets me 8, so I really have 2/3 times 8. Plus 2 times 4, that's 8. And then we have our minus 0 that we could write if you really wanted to. 2/3 times 8, that gets me 16/3 plus 8. And then we make common denominators, and that ends up being 40/3. So the area under the curve for this function is 40/3. Next up, we have the integral from 0 to pi for sine x dx. So take a second and take the antiderivative of sine. Hopefully you remember that that is negative cosine. Our interval is from 0 to pi, so we want to substitute in pi first. So negative cosine of pi minus a negative cosine of 0. Unit circle. The cosine of pi is really -1, so what we have is a negative -1 minus the cosine of 0. Cosine of 0 is 1, but we have that negative right there, so we have -1 right there. And then we've got a couple of signs to pay attention to. Negative is positive, negative, negative, that's plus 1. So really, this integral equals 2. Again, I'm going to let you pause and take the antiderivative of this right here just for practice sake. And here you go. When you take the antiderivative, I get 1/3 x to the third minus 3/2 x squared plus x. And then we have to remember that our interval goes from -2 to 3. So we take our antiderivative with 3 substituted in, and we've got 1/3 times 3 to the power of 3 minus 3/2 times 3 squared plus 3. Minus our lower limit put in, so 1/3 -2 to the power of 3 minus 3/2 times -2 squared plus a -2. Careful, make sure those parentheses are around this last because you are taking all of this and subtracting it from the front part. Go ahead, I'll let you pause and simplify that. That's a lot of fraction work. Practice, no calculator, try it on your own. After all that fraction work, hopefully you got 55/6 is the area under the curve for number 4. So I'm going to do number 5 and the next example in class. So we're going to go ahead and skip those. And we're going to look at mean value theorem and the fundamental theorem, or the second fundamental theorem of calculus next. So first up is the mean value theorem. And the mean value theorem says that if f is continuous on the interval from a to b, then there exists a number c on the closed interval from a to b such that the integral from a to b is equal to f of c times b minus a. So what this is basically saying is if this is the integral that I want to find right here, there exists some value of c, this is the c right here, that would create this rectangle that could be completed like this. So basically we are finding this value of c where I could take this piece right here and just flip it over and it makes a rectangle. So then I just have to do the height, which is f of c, this distance here, times the width, which is that a to b right there. Now, the mean value theorem just says that it exists. To actually solve for that f of c, we would use the average value of a function. And the way that we've gotten from here to here is basically we've just divided by this b minus a right here. So the average value of a function is really what you're normally solving for. So find the average value of this on the interval right here. So average value is that f of c that we're looking for right there. So f of c equals, this is my a, this is my b, 1 over 4 minus 1 times the integral from 1 to 4 of the function that I just had, 3x squared minus 2x dx. So of course we would take the antiderivative here. We can do some simplifying. This is really 1 over 3. And then this is times my antiderivative right here. So add to the power, so that's 3, divide by 3, and that would make 1. So that would be 1x to the power of 3. Add to the power here, that would be a power of 2, divide, and that would be negative 1x squared. And then it's a definite integral, so from 1 to 4. And then we would do what we were doing before, and we would just simply take this 1/3 and multiply it by f of b minus f of a. So 4 to the power of 3 minus 4 squared minus 1 to the power of 3 minus 1 squared. And then I'm just going to keep going along. 1/3. 4 to the power of 3 is 64. 4 squared is 16. So 64 minus 16 is what I get here. 1 minus 1 is just 0. So that's not going to do any good. So if this was 64 minus 16 right there, that's 48. So 48 times a third is what I end up with, and then that equals 16. So the f of c that I said exists up in the mean value theorem would be 16. That would be that height. Okay guys, let's look at the second fundamental theorem of calculus. What the second fundamental theorem of calculus tells us is basically that a continuous function is going to have an antiderivative. So if you look at the notation on the second fundamental theorem of calculus, notice that this is the derivative of an integral equals the function. Well, derivative and integrals are opposites of each other. Derivative and antiderivative, those are opposites. So what you're going to want to see here is you've got a number on the bottom and then some value that is a variable on top. And basically we're just going to substitute the x into whatever function it is here. But the idea is that the derivative and the integral are opposite operations. So the function is this piece right here. If your upper limit is a function itself, we're going to end up using a form of the chain rule, and I'll show you that. And then the upper limit needs to be the variable. I already said that. If the x is the lower limit, then we'll just use the property that we already know where it is the same as the negative of that. Okay, lots of talking. Let's actually do one of these. So here we have the integral from 0 to x. Evaluate the derivative of that integral. Well, derivative and integral end up going away, and then this x just simply needs to be substituted in. X squared minus 1 underneath that square root, and you're done. Now the next one is worded a little differently. It says find the slope of this integral right here. Well, hopefully you remember that slope means derivative, so it's basically saying the same thing than the one before did, where take the derivative of an integral, and this one's from pi over 2 to x to the power of 3, cosine t squared dt. So this is basically what it's saying, because slope and derivative are the same thing. Now notice my upper limit is not just x, it is a function itself. So this is where the chain rule comes in. We're going to do the same type of substituting that we did right here, where we have cosine x to the third raised to the second power. So because we inserted a function, we want to do that times the derivative of what we just inserted in. So 3x squared is the derivative of x cubed. And now we can just simplify a little bit, so that 3x squared cosine of x to the power of 6 if we do power to the power. So when we insert a function, it is that function times the derivative of that. That's our chain rule. Next up we have the same type of thing where we have the derivative of this right here, but notice that my function's on the bottom. So because it's on the bottom, we're going to use our property where it's actually the opposite. So this is the derivative of the negative 2 to sine x, and then we have cosine t plus 2 dt. Now that negative is just going to come along with us, and we're going to substitute sine x, our function, that should say sine x, into where I see t. Well, I have cosine sine x. That's a little weird. And then plus 2. Then we need to remember that we take that times the derivative of the function we just put in. Anytime it's the function that goes in, it's times the derivative for chain rule. So derivative of sine is cosine. So we multiply times cosine x. So there's not going to be much I can do to make this look nicer. I could distribute that cosine in there, and I would have negative cosine squared times sine x, but there's not really much that I'm going to be able to do there. I'm going to distribute the negative and the cosine here, so minus 2 cosine x, and that's about as pretty as I can make that one look. And then we will save this last bit for in class when I see you.